Nowadays, our world is facing a lot of problems. We have a lot of people on the earth. The population has been increasing very rapidly in the past decade. We have the population expansion problem.
And due to the climate change and the poor land management, and a lot of land cannot grow food anymore. So we have the food shortage problem. And we use a lot of energy, so we dig out from the land, so the energy resources also shortage. And
the majority of the population is living in the biggest cities.
So our living quality is getting lower and lower. So how can we improve the quality of our lives? Scientists has been pushing their technology boundary to the edge of the limitations, but we cannot have more. We cannot have a breakthrough until we go to the other direction. Then we work on the new material development, and then we have the breakthrough in nanotechnology. What is nano? Nano is a very small scale. And this is the length scale. Nano is a unit in the length. As we understand that human body's height is around 1 meter to 2 meters. Then a soccer ball, 0 point something. And then the size getting smaller, coins, bugs, and human hairs, rapid cells, and the virus. Then down to the very small, and then we can see the crystal structure and molecule and the atoms. And the nano size is in between 10 to the power minus 7 to 10 to the power minus 9 meters. So in this range, we simply use the unit nanometers. So in this range, scientists found a lot of material, they have different properties. And these different properties is not only depends on the size, but also depends on the format or the shape of the material. For example, here we have carbon. In carbon, we can make a carbon nano-onion, a multi-wall carbon nanotubes, graphene, a diamond, and nanohorn, bulky ball, and single-wall carbon nanotube, and the smallest carbon nanotube we can find. So among those material, only for carbon, then they have a lot of different properties. So this is the nano world. So welcome to Nano New Era. So my name is Bill Lee from College of Nanoscience and Technology, Suzhou University. My colleague, Professor John McLean, will join me to give you more details in how we can apply the nanotechnology in our daily life. So in this program, we separate into 6 talks. First one, we will start with the nanotechnology we can use in garment and clothing, then followed by the application in food and packaging, and then how we can use the nanotechnology to improve our living qualities. And then how we can use the nanotechnology application can solve some problem in the transportation. And we can use the nanotechnology can maximize our information technology collection. In final, but not least, we will talk about the future and how the nanotechnology can go to. Many years ago in our ancient time, our ancestor has been using the animal skin for clothing. And then they used for a long time. Later on, they found out they can grow cotton, and then they can get the insects to get silk so that they can make the clothes. And then that lasts for a long time.
Until the last century, in 1938, nylon was invented, and this changes the garment industry a lot.
Because nylon has a very good molecular structure and is very easy to produce and in a very low cost, so people can use it to produce different products, just like a carpet and stockings and even fashion.
But nylon also has some disadvantages. For example, it cannot keep us warmer. So people think about producing artificial wool, which is very similar to the real wool. People have also developed artificial leather, which is very strong and durable. Then, these change the garment and textile industry. They are no longer only depend on the animals.
So what kind of clothes we need? Of course, we need a very perfect clothing. Then we have, we want the clothes to have the season resistant or wrinkle free, heat isolation. Of course, we have the clothing we want to be look like more beautiful and more fashionable. And also these clothes can protect us from the UV radiation. And if we do some exercise and our sweat will not produce a very bad smelling, so it is antibacterial. And we have a lot of problem for the laundry, so this can be self-cleaning. And this, if we buy one, then we can use for a long time. And of course, this clothing can prevent water and oil. Can we have all those properties or characteristics for our perfect clothing? Yes. So what is the physical principle behind that? I think John will give you more detail.
Thank you, Bill. So as you probably guessed, the answer to a lot of the problems that we're posing here today is nanotechnology, or at least we're going to try to convince you that that's the answer to most of these problems. So just to take a step back and try to put everything into perspective, clothing is for our protection from the environment. And if we look at the natural world, the environment is the largest thing we come into interaction with, measured on scales of kilometers. And as Bill mentioned earlier, we, as people, are only a meter or so in height. And our skin is maybe our final line of protection. And the areas of skin are a couple centimeters. And if we zoom in on the skin, we'll see little cells. Those are less than a millimeter in size. Finally, the real line of protection is the cell membrane. It's only a couple of nanometers. And this gives us a range of length scales for the natural world that we can use as motivation to study the range of length scales in our society. For clothing, a piece of clothing is roughly a meter or a couple of centimeters, depending on how large it is. Clothing is made up of fabric, and a piece of fabric can be only a few centimeters in size. If you zoom in on the fabric, it's made of threads, which are roughly a millimeter or so, usually. You zoom in even farther, that thread is made up of little fibers, all entangled together, that are only about a micrometer. And zooming in on those fibers, they're made of little strands that are less than a micrometer in size. So we already have a little bit approaching nanotechnology just in regular clothing. We have similar orders of magnitude in scale. On the other hand, when we talk about the manufacturing process, we don't have a trend in terms of size, we have a trend in terms of complexity. As Bill mentioned earlier, Initially, people just wore animal skins. Very simple, very little to do. And then people invented sewing, so you can make more complicated garments out of that. And then finally, weaving. You can combine plant fiber to make large pieces of fabric. And then recently, we've had industrialized production with mechanized looms. And finally, as Bill mentioned, we have synthetic composites, new materials that can be engineered to fit certain properties. So the complexity of clothing design has increased greatly over human history. And when we think about what we want clothing to do, again, as Bill mentioned, we have a variety of requirements. It needs to protect us from cold. Maybe it should protect us from sunlight. We don't want to get sunburned. It'd be nice if it protected us from pollution. The PM 2.5 problem is something that most Chinese are familiar with. Oil and chemicals, we don't want them to get on our skin, so it'd be nice if the clothing could stop them. Finally, some people tend to sweat a little bit, and it would be nice if the clothes could clean that, so you don't get all funky and bad smelling. So this is kind of the motivation for looking at clothing engineering. So we have a set of natural scales in the real world. We have a set of natural scales in man-made clothing. We have an increase in complexity for manufacturing these clothing, and we have a wide variety of requirements. And we want something that will fit in this pattern. So we think the future is small. That's why we're giving these talks on nanotechnology, and hopefully you'll agree. So to give a little bit of an introduction to nanotechnology, there's several key features on the nanoscale that make it so interesting for possible applications. One of them is just the surface to volume ratio. We all know that the size of something, we call it the volume. It can be bigger or it can be smaller. But an object interacts through its surface. The more surface area it has, the more possibility it has to interact with other objects. That's if you fold the object out, you'll get its surface area. And as we shrink particles, as things get smaller and smaller, the ratio of surface area to volume increases. As the length scale becomes a very small number, this ratio gets larger and larger. So nanoparticles, there's very little material, but comparatively, there's a very large surface area. There's a maximum potential for interaction. And that leads to some very interesting behavior. In our daily lives, we're used to gravity being the most important force that influences us. You step off the edge and you're going to fall. But electrostatic force can be much stronger. The coupling strength for electrostatic force is much larger than gravitational force. We don't notice this because charge, electric charge, can be balanced. There's positive and negative charges. So most of the things in our life that we deal with are electrically neutral. But if we have just one electron missing from a particle, and that particle gets very small, it can be a much stronger force than gravity. So this is just a graph of the ratio of the electric force to the gravitational force between two particles of equal mass separated by 1 meter. And one particle has an extra electron, and one particle is missing an electron. And as soon as the mass of the particles goes below a microgram, the electric force becomes many, many, many thousands and millions of times stronger than the gravitational interaction. So the force that we're used to dealing with, we're used to overcoming gravity, that's why it's so hard to climb the stairs, is not a problem at the nanoscale. It's a different set of forces. It's electrostatic force that can become dominant. And we could use this to many effects. Something that on a large scale doesn't have that much extra charge, because it's so small, the electrostatic force becomes dominant. And we can make all kinds of nanostructured devices that operate effectively with only a small difference in electric charge. We'll talk more about this in specific examples as we continue in these lectures. Finally, there's the very way we describe the universe, the physics that we talk about. can be different at the nanoscale compared to our everyday life. We can describe a sports ball very well with classical mechanics. It has a position, and it's moving at some speed. And there's no ambiguity, there's no question about where it is and how fast it's moving. Everybody knows this. Everybody can measure it. But when objects get smaller and smaller and smaller, the position and the velocity become a lot more vague, a lot more hazy. We're not sure where it is. We're not sure where it's going. And this isn't just because it's small and it's hard to see. This is a fundamental feature of physics called quantum mechanics. Every object has something called a de Broglie wavelength that is an indication of what scale quantum mechanics is necessary. It's very easy to calculate the de Broglie wavelength. You take a number called Planck's constant and divide it by the momentum of the object. Momentum is mass times velocity. So as you have a very small particle with a very small mass, this momentum becomes very small. And this wavelength becomes larger. And when the wavelength becomes larger than the actual object, you need quantum mechanics to describe it properly. And at the nanoscale level, we're just bordering on the edge of where quantum mechanics becomes very important. So some of the things you think you understand about physics, because you're used to dealing with this big world that we live in, don't apply anymore at the nanoscale. So there's some very interesting ways we can use this. So that's just a very brief overview of some aspects of nanotechnology. Now maybe we can apply some of this to clothing. One area is making a water-repellent fabric. We live in Suzhou. The rainy season is coming up. This is a very interesting topic for people who don't want to get wet. Very interesting topic if you have little children and you don't want them to cry when they get wet. So here there are two videos, very short videos that I will show. This is a jug of water. It has some red dye in it. The red dye is just to make it colored red so it's easy to see. And they're going to first dip in a piece of paper, absorbent paper, into the water. It absorbs the water. Now it's colored red because of the dye. Not very strange, right? Everybody can do this at home. You pour water on paper, the paper gets wet. Amazing. In this video, the paper has been coated with a water-repellent material. So they're trying to get it wet, and it doesn't want to get wet. It's not absorbing any of the water. It doesn't even want to stay inside the water. It's trying to climb out. This is highly water repellent. So if you have clothing like that, and the clothing covers you, you're not going to get wet. All of the water will just run off the clothing. This type of thing is very motivated, in fact, by nature. We're all familiar with the lotus plant. It grows in the ponds around this university. And a lotus leaf is very water repellent. A drop of water on the leaf will bead up into a little ball. And this is because of nanotechnology that the plant has. We didn't build this, the plant grew this way. The surface of the plant, if you look at it under a very powerful microscope, has all these little bumps, tiny little bumps, that cover the surface of the plant and prevent water from flowing out flat. Water has a very high surface tension, doesn't like to spread out, and these bumps help force the water to sit on top of the plant. They're only about 10 microns in size, and even on these little 10 microns, there's even tinier nano-sized water-repelling crystals. So when water covers the leaf, it automatically beads up. It doesn't spread all over. The water doesn't touch this part of the leaf. If you if the leaf is on an angle, the contact angle of the water with this leaf approaches a critical value and it doesn't touch the leaf. This is a better example on a millimeter scale of a bead of water sitting on top of these small fibers. So if the leaf is tilted, this bead will roll. So not only will it prevent the leaf from getting wet, it will also clean the leaf because the rolling water will pick up all the dirt that's covered with the leaf. So if we can have clothing that's very water repellent, then if you want to clean it, you might just need to walk outside in the rain. Don't need to use the washing machine. Much simpler and healthy. You can go for a walk, become healthier, and clean your clothing at the same time. That's where this was discovered. So, on the subject of cleaning, sometimes when we are working out or in a stressful situation, we sweat, and that can cause bacteria to grow on us and our clothing, and things don't get so pleasant. So recently, people have found out that silver nanoparticles will kill bacteria. So this is a cotton fiber with silver treatment. And when you treat it, you don't need to wash it to get rid of the bacteria. The bacteria will die and fall off. So if you're running, you're working up a sweat. If you want to zoom in on part of your clothing, your sweat beads up on top of the cotton shirt or whatever you're wearing. And there's bacteria in your sweat because none of us are perfectly clean. And if you don't do anything, that bacteria will start growing on your clothes and make it smelly and stinky. But if we have silver nanoparticles in the clothing, then those silver nanoparticles will release silver ions that will kill the bacteria. Silver ions will destroy bacteria. And now there's no more problem. It's just water now. Water's okay. Water will evaporate. Bacteria won't evaporate. So if we can kill the bacteria, then the clothing will not become smelly, which is good, less work for us. So in studying this, there's lots of research into silver nanoparticles for antibacterial properties. Here's an example of some research at Funsum. Part of the problem, one of the reasons why we don't all have clothing with this, is that it's hard to support the silver nanoparticles. The nanoparticles themselves are extremely small, very, very small. We need to support them on something, otherwise they'll just fall out of the clothing. And the question of what to use as a support is a big question. So here they have a metal oxide. I think it's titanium oxide. And if you look at it in an elemental map, this green is titanium. So the silver nanoparticles are supported on the outside of this titanium oxide. Titanium oxide is a good choice because it doesn't really rust, it doesn't poison people, it doesn't corrode. It will last a long time and it's safe. So if you accidentally eat it, no problem. And then we want this stuff to spread out in water. This is exactly the opposite of the lotus leaf. Exactly the opposite of the water-repelling fabric. We want these things to spread out evenly through your sweat so they get in contact with the maximum amount of bacteria. So we coat this cluster with an ultra-thin film that is hydrophilic. Philic part means water-loving. Philic is love. Phobic is fear. So before, the lotus leaf was hydrophobic. This is hydrophilic. It will spread out evenly. And if we look at it again, here the orange color is exactly the same structure but showing the film. The film is all around the outside. And these particles will evenly disperse in water to maximize their contact with bacteria. So this is a promising application. And I think Bill will talk some more about some other applications of clothing.
To protect our bodies away from the UV, some nanoparticles can enhance this function, just like titanium oxide, iron oxide, and zinc oxide. The principle behind is when these nanoparticles explode to the UV light, and these UV light strike inside, and inside that electron and hole, they get enough energy to combine, or they can go to the surface to combine with the other elements, to combine with other chemistry to form the different compounds. So that means the UV light just absorbed, it cannot go through these nanoparticles. If we make all those nanoparticles on the surface of the fiber, just like this coating, and we make it a lot, so this will protect us from the UV light. Nanomaterial, just like the polymer nanomaterial, can also prevent very huge impact strike, just like the bullet. This is the application in the bulletproof. You can see this picture shows the bullet come into this material and stop inside. And not only this, but also in a very short distance. You can see this is the structure, how they stop the bullet. Another application that we can use the nanotechnology in our clothing that make this electrical device. For example, we can use a flexible solar cell, stick on the surface of our clothing, then we'll charge up our equipment. This is very good for the military when they are working or they are fighting in the battlefield, so they can charge up their equipment. And we also can apply another electronic products inside the clothing. For example, we can integrate the mobile phone inside, or computer, or any kind of sensor. Or we use the different sensor so that to work with the other equipment, so can provide us warm in winter, cool in summer. So that is a more general application in clothing. But what about the mask? Can we use this for the mask to prevent the 2.5 pollutions, PM 2.5? Yeah, we can use that. Let's look at this. This is the sand, very fine sand from the beach, and the size is around 19 micrometer in diameters. And this is the human hair in the size of 50 to 70 micrometer in diameter. And this is a PM10. Most of them are the dust or all this, but it's very heavy and it does not airborne. But when these particles are getting smaller, you can see that it's PM 2.5, that means the size around 2.5 micrometer. All of these are mainly the combustion from the car, all this industry machine, and all these heavy metals. This will affect our health. So if you use the graphene-based nanopores, this gas filter can prevent this. So this is the structure, layer by layer of the graphene, and with all this pore in nano size, this can prevent the PM 2.5, but let the oxygen gas go through. So in summary of this nanotechnology application in clothing, now we can see that the silver nanoparticle, it has antibacterial properties, and the iron nanoparticle can conduct the magnetic properties. The zinc oxide and titanium oxides can prevent the UV light and the other application. And titanium oxide and manganese oxide can prevent us from the chemical and biological attacks. And silicon oxide and aluminum oxide nanoparticle can repel the water. Indium tin oxide nanoparticle can protect us from the electromagnetic wave and the infrared. And ceramic nanoparticle can increase the resistance to abrasion. And the carbon nanoparticles can increase the resistance to abrasion and some chemical resistance. And the clay nanoparticles can be a very good resistant to heat, chemical, and electrical. This we can apply to use for the firefighter. So, because we apply the nanotechnologies in the clothing, so our cloth is no longer so simple. It can provide us the self-cleaning properties and anti-static. Then if we do, we have a sweat, and this is the auto fight, so you don't get any bad smell, and anti-pollen, and the flame resistance, so it's not easy to get on fire. And the functional finishing, just like a wrinkle-free and strain and static resistant, and protection against chemical and biological threat, against spraining of functional nanofibers and ions. And it is very smart, comfortable, and maybe some medical application. It can be a very functionalized fabric for UV protection and the odor. So this is the advantage of our new technology in using in garment and clothing. Thank you very much.
Any questions? Yes.
My question about the civil nanoparticle. So the civil can kill the bacteria. So it will also kill our healthy cell of our screen.
That's a good question. It doesn't seem to. One of the reasons why you don't have clothing covered with silver nanoparticles is because we're not completely sure yet. But it seems that silver nanoparticles are mostly only affect bacteria and not more complicated cells. But we do need more long-term studies to make sure this is true. So at the moment, it looks like it doesn't have a bad effect on your health. But we're going to do some more research before we cover you with silver nanoparticles to make sure. Perhaps somebody has a question? Yes?
Why is the surface to volume ratio is so important to the properties of a particle?
Because chemical interactions, any kind of chemistry, chemical bonding, and those kind of things occur at the surface. You can't have a chemical bond from the middle of one particle into the middle of another particle. All the chemical interactions occur at the surface where two particles are touching. But a lot of the other fundamental forces, like gravity, those affect the volume of a particle. So as the surface area gets larger compared to the volume, the chemical interactions become much more significant than the volume interactions. There is a chemical interaction between my hand and between this desk. But because my hand is large and the desk is large, gravity that affects the volume is much stronger than the chemical interaction between the two objects. If I had a nano-sized hand and this was a nano desk, it would be the chemistry that would dominate what happens instead of gravity. Is there a question? Yes.
I want to know how you ensure that the cloth is both anti-water and anti-oil at the same time, because the water and oil are on the opposite side.
You could have two layers. You don't mix, the oil and the water don't mix on their own. You're only going to be exposed to one or the other. Probably you don't need clothing that needs to be both. If you're getting splashed with oil, it's probably because you work in the kitchen and you're cooking. And if you're getting wet, it's because you're outside. Unless you're cooking a lot outside, I don't think you need both. If you did need both, you could do it in layers. You could have an anti-water surface on the top and a small gap, and then an anti-oil surface.
Well, is it efficient to protect from both?
Probably not in that way. It depends on usually people are going to get splashed with a lot more water than oil. So the anti-oil is something that will be easily removed during cleaning. not necessarily, you don't usually get soaked in oil. If you do, you have a very strange lifestyle. So I think the focus would be on on water repelling. And you would only need a serious oil repellent clothing in a very specific situation.